Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 13, discusses the basis of nuclear magnetic resonance spectroscopy. In Masterclass 4, we discuss the Zeeman effect, which is the interaction between the internal magnetic moments of electronic quantum states with external magnetic fields. Nuclei that possess quantum spin also have magnetic moments that can interact with externally applied magnetic fields. This interaction forms the basis of nuclear magnetic resonance, or NMR spectroscopy. Owing to the m sub I dependence of the interaction energy, application of an external magnetic field lifts the degeneracy of nuclear spin states. NMR spectroscopy measures transitions between these spin states. Since the nuclei of different elements have different magnetogyric ratios, the energy separations between spin states, and therefore the transition frequencies, are different for each element. For example, because the value of gamma for hydrogen is approximately 4 times larger than that of carbon-13, so too are the transition frequencies. Typically, these transition frequencies are in the radio wave region of the electromagnetic spectrum. It turns out that not all nuclei of a particular element resonate or have transitions at exactly the same frequency. When an external magnetic field is applied to a molecule, the electron density around the atoms begins cycling so as to produce an opposing magnetic field. Thus, the effective magnetic field experienced by the nucleus is slightly less than the applied magnetic field. The higher the electron density around a given nucleus, the weaker the effective magnetic field experienced by that nucleus, which results in a lower resonant frequency to induce transition between spin states. This phenomenon is referred to as electron shielding. Introducing electronegative elements to a molecule serves to remove electron density from electropositive elements. As a result, the electropositive nuclei experience more of the applied magnetic field, and transitions between spin states are duly shifted to higher frequency. This process is known as de-shielding. It then stands to reason that the exact frequency at which a nucleus resonates depends on its electronic environment. Thus, chemically different nuclei will resonate at different frequencies. For example, consider the carbon-13 NMR spectra of acetone and propanol. Both molecules have the chemical formula C3H6O. The difference between them is the location of the carbonyl group. Owing to symmetry, the two methyl groups of acetone are chemically equivalent. Both have exactly the same electronic environment and therefore have exactly the same transition frequency. However, the carbon atom in the carbonyl group is in a different chemical environment than the two methyl groups. It is closer to the oxygen atom than the methyl carbons and is therefore more de-shielded. As a result, the carbonyl-carbon resonance is shifted to much higher frequency. In propanol, all 3 carbon atoms are in different chemical environments. Carbon atom 1 is closer to the oxygen atom than carbon atom 2, which is again closer to the oxygen atom than carbon atom 3. As a result of the 3 chemical environments, 3 carbon-13 resonances are observed with chemical shifts based on proximity to the oxygen atom. In NMR spectra, chemical shifts are reported rather than absolute frequencies to offset error introduced by differences in magnetic field strengths for different NMR instruments. The frequency difference for the signal of interest relative to a standard reference compound is measured and reported relative to the reference transition frequency. Since frequency differences are typically on the order of hertz, while absolute reference transition frequencies are on the order of megahertz, chemical shifts are reported in parts per million, or ppm. We find that electronegative groups are not the only cause of chemical shifts in NMR spectra. Doubly and triply bonded carbons and carbon atoms in aromatic ring systems also experience significant chemical shifts. So too do sp2 carbons bound to electronegative groups. Carbonyl groups, for example. We find that specific types of carbon chemical environments resonate in distinct chemical shift regions. This provides an excellent metric for determining chemical structure. At first glance, the chemical shifts of carbonyl carbons might seem anomalously large. we find that ketone carbons typically exhibit chemical shifts just above 200 ppm, aldehyde carbons just below 200 ppm, and carboxylic acid derivatives typically resonate in the 160 to 170 ppm region. This apparent de-shielding can be explained in terms of the resonance structures of the carbonyl group. The resonance contribution from the charge-separated species shows the extent to which electron density is drawn away from the carbon atom in the carbonyl group. In carboxylic acid derivatives, the heteroatom can donate some electron density back to the carbonyl carbon, thus shielding it slightly compared to the analogous ketone and aldehyde carbons. We can also identify specific chemical shift ranges for the different chemical environments of hydrogen nuclei. Since carbon-containing molecules often contain hydrogen atoms too, the combination of carbon-13 NMR and proton NMR is a powerful tool for determining molecular structure. As was the case with carbon-13 NMR, proton NMR also exhibits chemical shifts that appear to be out of the ordinary on first glance. For example, carboxylic acid protons and protons bound to aromatic carbons are especially de-shielded compared with most other proton chemical environments. The chemical shifts of carboxylic acid protons can also be explained in terms of resonance structures. In this case, the same resonance structure that donates electron density to the carbonyl carbon results in de-shielding of the acidic proton. If we compare the chemical shift of the OH proton in benzyl alcohol to that of the OH proton in benzoic acid, the importance of this electron density donation is apparent. The spectrum of benzyl alcohol also provides a good example of how much larger chemical shifts of aromatic protons are compared to alkyl protons. Here we see that the 5 benzyl protons resonate at approximately 7.4 ppm, while the 2 methylene protons resonate at approximately 4.5 ppm. Note that the relative intensities of proton NMR peaks provide the relative number of protons in distinct chemical environments. Owing to their conjugated pi systems, aromatic compounds generate cycling ring currents when subjected to external magnetic fields. This ring current produces a magnetic field that increases the effective magnetic field experienced by protons attached to the ring. The effect of the ring current is apparent when we compare the proton NMR spectra of cyclohexane and benzene. The 6-carbon ring of cyclohexane does not produce a ring current when exposed to a magnetic field, and the attached protons resonate at approximately 1.5 ppm. Benzene, on the other hand, does generate a ring current, and its proton resonances are shifted downfield to 7.5 ppm. Chemical shifts are not our only means of characterizing molecular structure in NMR spectroscopy. In Masterclass 14, we will discuss how adjacent magnetic environments can influence NMR resonances. See you next time.